Every AI computation draws real electricity and produces real heat. Though living in software, AI is strictly bound by physical constraints of power and water. The core engine doing this numerical work is the GPU accelerator chip. In physical terms, that computation directly manifests as thermal energy. Generation pushes that boundary even further, well past a full kilowatt per chip. Moving over 1,000 watts of thermal energy away from a few square inches of surface area without destroying the component is a severe mechanical challenge. Standard conventional processors do not generate this kind of localized heat density. This concentration requires entirely bespoke cooling infrastructure. Computational throughput is now limited more by physical laws of heat dissipation than by logic design. At the leading edge, AI engineering has to solve a thermodynamics problem before it can solve a software problem. When you scale from a single chip to an entire server rack, the physical footprint multiplies those constraints. Take a current GB200 NVL72 rack. This single chassis houses 72 Blackwell GPUs. Together, they generate up to 140 kilowatts of heat, equivalent to 12 household electric ranges running at full power inside a tall refrigerator. Traditional air cooling is mathematically incapable of managing this load. You cannot push enough air through the dense space to offset that heat. This makes direct liquid cooling a mandatory structural specification, not an optional retrofit. Plumbed directly into the facility, active liquid loops rely on chilled supply lines delivering cold fluid and warm return lines carrying extracted heat away. These systems integrate deep inside the chassis, pressing directly against the silicon to capture energy at the source. Operating these systems requires significant physical weight and mechanical exactness to connect the active pressurized loops safely within a live server environment. Data center architecture must now be designed around high-pressure fluid dynamics just to keep the silicon alive. Beyond the physical plumbing, the energy drawn through these racks is dictated by two very different software workloads. The first is training. Building a large language model is an intensive, one-time thermal and electrical event. Training the GPT-3 model in 2020 consumed roughly 1,300 megawatt-hours in a single isolated spike. Projections for upcoming frontier models reach tens of thousands of megawatt-hours per training run, representing a tenfold increase in energy demand. There is wide uncertainty in those estimates, as the final number depends heavily on cluster efficiency and hardware failure rates during the run. Then there is inference. This is the continuous, opposing side of the ledger, occurring every single time a user queries the trained model. Analysts estimate a widely used assistant requires hundreds of megawatt-hours daily, compounding year-round. At the query level, simple text draws a fraction of a watt-hour, while image generation requires several watt-hours. A typical AI query uses 10 times the energy of standard search. Facility engineers are left to design electrical systems capable of supporting both massive episodic shocks and relentless daily attrition. Supplying those continuous loads requires scaling our focus out to total facility power, which extends far beyond the IT equipment itself. The industry tracks this efficiency using power usage effectiveness, or PUE. PUE is calculated by taking the total facility power draw and dividing it strictly by the power used by the IT equipment. This chart illustrates an industry average PUE of 1.5, where a third of electricity is lost to cooling and lighting. When operators put high-density AI into legacy buildings, that cooling ratio balloons as extreme heat overwhelms older airflow designs. Beyond the electrical load, AI infrastructure requires a significant supply of material water. This is measured as water usage effectiveness, or WUE, tracking the liters of water consumed per kilowatt-hour of IT energy. The primary consumers of this water are evaporative cooling towers, which reject facility heat outward through large-scale evaporation. Operators mitigate this using closed-loop liquid cooling designs, aiming for zero ongoing water consumption. But external chiller units must work harder, requiring more electricity to reject the heat, driving the facility's PUE back up. Data centers are constrained ecosystems. Pushing computational density higher forces the facility into direct competition with local municipal power grids and groundwater supplies. This massive power draw inevitably leads back to the environmental reality of the carbon footprint. Executing the exact same computational workload will yield drastically different carbon emissions, depending entirely on the local grid mix powering the facility. Identical energy inputs yield vastly different outputs. A facility on a coal grid generates carbon intensity up to 50 times higher than a nuclear or hydro grid. Variations in reporting Scope 2 emissions often obscure these physical realities, making direct comparisons between operators difficult. But beyond emissions, the push for thermal efficiency is overwhelmingly driven by commercial realities. At the commercial scale of multi-billion-dollar inference, a single percentage point of thermal efficiency translates directly to tens of millions of dollars in operational savings. This creates what economists call a rebound effect. Newer generations of GPUs consistently deliver far more computation per watt of energy. However, by making inference cheaper and more efficient on a per-query basis, operators inherently expand the total market and use cases for AI applications. The efficiency does not reduce the load. Total AI energy demand will persistently climb because hardware improvements expand utilization faster than they reduce overall consumption. To review the complete facility data and read the full report on thermal infrastructure, visit ProReadyEngineer.com.